Hello everyone, welcome to lecture 2 of Stereoisomerism. So in this lecture, let's start with our first concept, Enantiomers and Diastereomers. So when we split isomers, so isomers can be classified into two types, constitutional isomers and stereoisomers. And constitutional isomers, we already told, are compounds with different connectivity. Stereoisomers are the ones with same connectivity but are not superimposable. But stereoisomers themselves are two types. One is enantiomers and diastereomers. Enantiomers are non-superimposable mirror images. Diastereomers are also non-superimposable, but they are not mirror images of each other. So enantiomers are stereoisomers that are mirror images, and diastereomers are stereoisomers that are not mirror images. Now consider the structure of cis and trans 2-butene. So notice the structure of cis 2-butene and trans 2-butene. Why is cis? So cis is because the major compound is on the same side and the major compound is on opposite side, so that's why we say it's a trans compound. So these are also stereoisomers, but they are not mirror images of each other. Notice that just because you keep a mirror here, it does not mean that both are the images are mirror images. So these images are called diastereomers. So enantiomers generally have identical physical properties, but diastereomers have different physical properties. So how can you differentiate between enantiomers and diastereomers? Is one way is to look at the structure, and if you look at it and if they are not mirror images of each other, they are also diastereomers. And one another property in terms of their physical property is that they have different physical properties with respect to the structure that they do have. Now, so use this example now and try to find whether each of the molecules that are given here are either cis, either enantiomers and diastereomers. So pause the video right here and try to solve this problem. Next, let's talk about stereoisomeric relationships. So consider a simple cyclohexane that has 3 substituents. With 3 substituents, you can draw up to 8 stereoisomers, 8 different stereoisomers. So because there are 3 stereocenters here, so the total number of possible stereoisomers are 8. So the relationship, how do you consider the relationship among enantiomers and diastereomers, is that notice in this 8 stereoisomers, there are 4 pairs of enantiomers. So notice that this is one pair, this is the second pair. Notice that these two are mirror images of each other. Every one that I am drawing in the rectangle is the mirror image of each other. So these are all examples of enantiomers. So there are 4 groups of enantiomers that we have here. So basically think of this, that each kid here has 7 siblings, but where one of them is there going to be a twin. So one of these images will be the exact same as the other image. So best example of that would be to take a look at the first one. So in terms of the first one here, there is exactly no clear sense that they are exactly mirror images of each other. So if you rotate the second molecule, you will still end up getting it the same molecule. So you don't get any other different molecule. So these are examples of where you would see the difference between the stereoisomers and enantiomers and diastereomers. Now with this in consideration, what is the total number of possible isomers for any compound? That generally is determined by the number of chirality centers that the molecule has. So here the maximum number of stereoisomers for any given molecule is 2 power n. So where n represents the number of chiral centers. For example, let's take this problem and let's try to find all the chiral centers in this molecule. So you already know the procedure. There should be 4 distinct groups. So this is 1. You have 2, 3, 4, 5, 6, 7, 8, and so that's a total of 8. So these are the 8 different parts that you do have. Now with these 8 different parts, so that is total of 8 chiral centers, 8 chirality centers. So in terms of the number of stereoisomers, it should have 2 power 8 stereoisomers. So that is about 256 stereoisomers. So there are 256 stereoisomers. So let's next talk about symmetry and chirality. So is it possible that a given molecule is a stereoisomer every single time? So if you have any compound with only one chirality center, that one will always be a chiral compound. So if you have just one chirality center, that means that is a chiral compound. But when you have more than one chirality center, a compound may not be chiral because it may have what we call the plane of symmetry. For example, let's consider the two molecules that you have here. When you consider these two molecules possess two chirality centers. These are the chirality centers for each of them. Now with these chirality centers, the problem here is that when you take a look at this molecule, is there a plane of symmetry that is possible here? So which means that when you cut it or when you put the exact mirror in the exact middle of the molecule, well, you see mirror image on the other side. So if I keep a mirror here, I'm not seeing a mirror image, so it's not a, so this is a chiral molecule. But notice here, if I keep a mirror between these two molecules now, notice that this is a mirror image. So this is what we call an achiral compound. So this is an achiral compound because it has a plane of symmetry. So plane of symmetry can be defined as the plane that divides the molecule into two mirror images. So when you keep it in the center, it creates a mirror image on the other side. So this is an example of a molecule that has chiral centers but can be achiral. So the trans isomer here is chiral, but the cis isomer is achiral. So if the molecule has a plane of symmetry, it will be achiral. So the plane of symmetry basically means that it will be superimposable on the mirror image. Therefore, it is not a chiral compound. So molecules that with an even number of chirality centers that have a plane of symmetry are called Miso compounds. For example, the molecule that we talked about here is a Miso compound. So any way to test if a compound is a Miso compound is to see if it is identical on its mirror image. So if you put a mirror right at the center of the molecule, if you get the same exact molecule, then that is a Miso compound. So draw the mirror image of the cis isomer and show that it can be superimposed on its mirror image. So that by its nature results in a Miso compound. So by definition, when a compound is identical to its mirror image, it is not chiral. So remember this point, very important. So when a compound has a mirror image, is identical to its mirror image, then that is not a chiral compound. So there is also one another process where we have plane of symmetry, is what we call a reflectional symmetry through inversion. So when you have reflectional symmetry, what does that mean here? So the molecule to the right here has two chirality centers. This is number 1 and this is number 2. Now when you have no plane of symmetry specifically here, but when you rotate the molecule on this axis, for example, let's say if I rotate the molecule on this axis, it creates the exact same image on the other side. So exact same molecule on the other side. So because this still does not have a plane of symmetry per se, but it does have a reflectional symmetry, where the reflection of the image can also cause the same molecule to form. So this is an example of a molecule that has reflectional symmetry through inversion about a central point in the molecule. So this is the central point and it has reflectional symmetry. So which means that if I move this downward, then this goes upward, the molecule will stay the same. So this is the idea behind the molecule to the right that you have here. So overall, what are the things that make a molecule chiral or achiral? So the presence or absence of rotational symmetry is one thing that is irrelevant to chirality. So if a compound has plane of symmetry, it is achiral. If the molecule does not have a plane of symmetry, it is chiral. So a compound without a plane of symmetry will usually be chiral, but there are exceptions when you have an inversion center. So this is the example. So these are examples of Miso compounds. How do you know these are Miso compounds? So this is plane of symmetry here. This is the plane of symmetry and this is the plane of symmetry. So you can draw the plane of symmetry at the center of the molecule and it becomes the mirror image on both sides. So this is an example of Miso compounds. So Miso compounds generally are molecules that have less than the predicted number of stereoisomers based on the 2 power n formula. So because Miso compounds will have 2 power n minus 1 number of isomers or less than that as well. So now use this problem now, and they are asking you here, draw all possible stereoisomers for each of the following compounds. First, find the number of chirality centers. Second, based on the number of chirality centers, now draw the stereoisomers. And for each possible stereoisomer should only be drawn once. So that is the request that they have here. So use this principle now and try to solve this problem. Next we have another way of representing molecules called Fischer projections. So Fischer projections can also be used to represent molecules with chirality centers. So one of them is to remember that when we write Fischer projections, we write molecules under horizontal lines and vertical lines. So the intersection point between horizontal and vertical represents the carbon. So the intersection point between the vertical and the horizontal line represents the carbon. So here you have a vertical line and a horizontal line. So this intersection point represents the carbon. So how do you know which lines are pointed towards which side? So one way of knowing that is to look at each line. The horizontal lines are the ones that are facing you upward. So the horizontal lines are the ones that are coming out of the page or facing up, and vertical lines are the ones that are going into the page or facing down. So here ethyl and methyl are facing down, H and OH are facing up. So this is an example of a Fischer projection. So whenever you see a Fischer projection, remember that the vertical lines are the ones that face downward, the horizontal lines are the ones that face upward. So this is the idea behind Fischer projections. So each intersection represents a chiral center or a chiral carbon. Let's write it that way. So we write carbons that do not have, that are not chiral, that are achiral, right? So we only write carbons that are achiral. Any chiral carbon is written as an intersection point, so which means that this structure here has 2 chirality centers, this structure here has 3 chirality centers, this structure here has 4 chirality centers. So if you already know some biology, you would already realize that these are molecules of sugars, right? So these are common structure of sugars. So this structure here is glucose, so this is pentose, this is tetrose. So these are examples of sugars that are written under Fischer projections. So most common Fischer projections are generally used for sugars because they are easy to write it down. Now Fischer projections can also be used to assess the stereoisomeric relationships between the molecules. How can you assess the stereoisomeric relationships? Is one way to look at which direction the molecules are. So between these 2 molecules, the bromine is on the exact same side, but they are mirror images of each other. These are enantiomers, and when you have bromine on the opposite sides of the chiral axis, we call this diastereomers. So diastereomers and enantiomers. So these are ways we can represent by using the common Fischer projections. So use this principle now and try to identify the configuration of the chiral centers in each of the following compounds that are given. So let me do the first one so that you can do the second one. Remember, horizontal comes out of the page and vertical goes into the page. So which means that this single compound here can be written as NH2 facing up, H facing up. This is COH double bond O facing downward. This CH2OH facing downward. Now you don't want H to be on the top to write down the configuration, so you want it to be on the bottom. So when you want it to be on the bottom, what do you do now is you rotate it 90 degrees. So how do you rotate it here? Now rotation involves converting this structure into a normal structure first. So let's take a look at this structure and let's try to write it down. So when you look at this structure, how do you look at it? Is you look at it from this direction. When you look at it from this direction, hydrogen is in the front, NH2 is in the back, COOH on each side, right? So when you write it down, it will look somewhat like this. What we are trying to do here is we are trying to convert that into this format. So how would you write that? Is this comes right here, this comes right here, NH2 is on the back side, so it will go here, and H will come here. So it becomes H, NH2, CH2OH, and COOH. So this is how you can convert a general structure into a normal configuration way of a structure. Now we have written the structure in this format now. So we have NH2, H, COOH, and CH2OH. Now based on this structure, H should be in the back, so rotate it across the horizontal axis. So when you rotate it, it becomes NH2, H, CH2OH, COOH. So this is the carbon here. So based on what we see here, so what can we write now? So now let's start assigning priority for each of these. So the largest one here is nitrogen, so that gets the first priority. Next, between the two carbons, this is connected to two hydrogens, but this is connected to two oxygens. So this gets second priority and this gets the third priority. So when you write it down in this structure now, you get a clockwise structure, so which means that this is an R configuration. So this is an R configuration. So this is how we can write it down. So use this principle now and try to do the rest of the problems. So pause the video right here and try to do B, C and D here. Next, let's talk about conformationally mobile compounds. So molecules that can rotate around a single bond are called conformationally mobile compounds. So if you recall the Gauss rotational configuration where for butane, CH3 and CH3 are right next to each other, this is an example of conformationally mobile compound, but the other side will also become the same. So realize that these conformations are also chiral but are enantiomeric, which means that they are mirror images of each other. So but because the rotamers are interchangeable via bond rotation, butane by itself is not a chiral compound. So remember that these are compounds where conformations are chiral but the molecule is not chiral. So these are examples of conformationally mobile compounds. Next one are interconverting enantiomers. For example, when you take both possible conformations for cis 1,2 dimethyl cyclohexane, this is one and this is the other. These conformations are also chiral and also enantiomeric when you look at it. So when you draw a mirror image, these are also mirror images of each other. So these are what we call interconverting enantiomers. Again, these conformations are interconverting overall, but this by itself is an achiral compound, The reason is because this has an internal plane of symmetry. Because it has an internal plane of symmetry, we do not call this a chiral compound, but the configuration is chiral. Remember the differentiation here. The configuration is chiral, but the molecule is not. Next ones are molecules without chirality centers but have chirality. One example is Atropisomers, where these are stereoisomers that would be interchangeable through the rotation of the sigma bond, but the bond here is unable to rotate. So this bond here is unable to rotate. Because it's unable to rotate, it produces two different configurations, S and R, even though the molecule by itself does not have any chirality center anywhere on the compound. So these are examples of Atropisomers. Next one is Alenes. Alenes are compounds that possess two adjacent double bonds. So they may or may not be chiral depending on the substituents. If they have two different substituents, then we can call these examples. So if there are two groups on each end of the alene are different, then that will be a chiral compound. Notice that these two structures are chiral compounds of each other, provided that the structures on each of them are different from each other. Only then we can call this chiral compounds. So these are alenes. Next, how do you separate enantiomers? One method commonly used to separate enantiomers is distillation. Distillation, when you have different physical properties, you can separate them with different boiling points. That process is called distillation. The most common process that is done is for petroleum, crude oil. So crude oil is refined using a process called fractional distillation, where at each point of temperatures one single part will come down. So that is an example of distillation. The other process where we have different solubilities, we can escape them. That's called recrystallization. So recrystallization is the process where we can separate the compounds with different solubilities. So one molecule undergoes crystallization at one point and the other molecule crystallizes at another point. So but these methods cannot work with one enantiomer from its racemate, because the molecules by themselves have identical physical properties. So because they have identical physical properties, it's hard to separate the enantiomers. One of the first methods developed was in 1847. Pasteur performed the first resolution of enantiomers from a racemic mixture of tartaric acid salts. So the different enantiomers formed different shaped crystals and they were separated by hand using tweezers. Obviously, this method doesn't work for most pairs of enantiomers because most do not crystallize correctly. So another method that is used is by using what we call a chiral resolving agent. So a chiral resolving agent is a molecule that can resolve the compound based on its chirality. So the different physical properties of these diastereomers allow them to be separated more easily when you attach them to a chiral resolving agent. So this is the idea here. So one another method that we use to separate compounds is a process called affinity chromatography. So we use a glass column, we pack it with a solid substance, and that acts as an absorbent, and the mixture passes through it. If a chiral absorbent is used, then the enantiomer will interact with differently and travel through the column at different rates, allowing them for individual collection. So remember the term adsorbent. They are not the same as absorbent, but adsorbent is a different term than adsorbent. So this is the very common method of resolving these enantiomers. Why do we need to resolve these enantiomers? Is because enantiomers have different pharmacological properties. So using one enantiomer might be effective. Using the other enantiomer might not be effective. So that is one of the reasons why we cannot resolve them. We have to resolve them into separate enantiomers. So let's look at the last designation or the last designation. We use this for alkenes. Remember that EZ designation is something we only use for double bonded carbons. So for molecules with different groups attached to the C double bond C, we use the EZ notation instead of cis trans notation. So when you have different groups attached, this is the idea where we use different notations when you have different groups attached. When you have similar groups attached, we can still use cis-trans notation, but when you have different groups attached, we'll have to use EZ notation. So cis-trans only works if there is a like group on each carbon of the alkene. For example, if you have CH3, then it will work. If it's not, then it's not going to work. Now, how do we assign EZ to the C double bond C? So we prioritize the groups based on the two sides of the double bond based on the atomic number. For example, let's take these two sides and these two sides. Here you have an ethyl group, so you have a carbon here, here you have a fluorine, you have hydrogen here, you have nitrogen. So fluorine gets priority over carbon and nitrogen gets priority over hydrogen. So we only take the priority ones. So now we have designated priority for fluorine on this side and nitrogen on this side. If the prior group, so the ones with the higher priority, if they are on the same side, we call that Z isomer. If they are on the opposite side, we call that E isomer. So this is the difference between E and Z isomers. So if we call them Z if they are on the same side, if they are on the opposite sides of the plane, so we consider this as the plane. If they are on the opposite sides of the plane, we call that an E isomer, coming from the German word zusammen and Entgegen. So these are the two terms that are used to separate alkenes based on EZ designation. So let's try the first compound here. Here you have carbon here, so this is the plane here. On the other side we have hydrogen, on this side we have this, so this gets priority. Next, on this side you have a carbon that's connected to two carbons, but here the carbon is connected to one carbon and a hydrogen, so this gets priority. So both are on opposite sides, so we say that this is an E isomer. So this way, try to designate all the other compounds based on this structure. So pause the video right here and try to solve these problems. So with that, we end our lecture on stereoisomerism. So I'll see you again in the next lecture.